All good? Okay. All right. Hi, everyone. Welcome to the talk. We're going to be doing realistic and lightweight baked water simulations for games. So my name is Devin Penny. I am a senior simulation programmer at Epic Games. Done a lot of work on fluid simulation. I wrote Niagara Fluids, if some people are familiar with that. We're going to talk about this new tool set that we made for baking water simulations that was used on the Witcher 4 Unreal Engine 5 tech demo that everyone saw here. And we use it to add these realistic and super efficient rivers to that really rich environment. And also, beyond what we did in that demo, we're going to talk about some other uses where we utilize these bake simulations for coupled chaos simulations for doing like water interactive gameplay elements. Okay, so this is just some clips from the Witcher 4 demo that use the water. These are all running, as you all know, at 60 FPS on the PS5, and these rivers are living in this super complicated environment that we all learned about with the nanite foliage and all these other elements that make it really interesting to try to integrate something else that is typically very computationally expensive, water. So it was a really big challenge to make it work at perf with a very small budget and also just integrate it into this world because of the really complex lighting and other environmental aspects of it. So this is a brief overview of the tool set, doing baked fluid simulations. And we're using a Niagara fluid simulation under the hood for doing the river using shallow water. And we use those to bake out the simulations to textures, use them in game, use them for rendering, use them for physics. And this is a new experimental feature in 5.6, part of the Water Advanced plugin. So that's where you would want to find it. Okay, so here's just kind of an overview of the talk. So we're going to start by talking about that baking workflow and kind of drive that by the Witcher 4 kind of examples that we have. And we're going to kind of go through the entire process of the baking. And then we're going to go on to sort of the water simulation concepts. Just briefly, this is not the main part of this talk, but it's really helpful to sort of understand how water simulation works for things like this in order to know the limitations and the advantages of a system like this. Finally, we'll talk about the surface shaders and secondary particles, which are really responsible for bringing this whole thing to life, because otherwise, you only have this very static-based simulation. And the last thing we'll talk about is that chaos integration to show how we can use the baked river data for gameplay elements by coupling the velocities you get from the river with chaos. So first, we will talk about the baking workflow. So here is just like an overview of the general editor workflow for doing the baked simulations. In purple, we have the first stage, which is just what a lot of people who are used to working with water bodies in the engine might seem familiar with, is just laying out your rivers, using the river splines, modeling the terrain, modeling your landscape, and just making sure that you have something where water can flow down it. So that's really all that matters here. And we do rely on those spline-based water bodies to sort of guide the river. We'll talk more about that later, about how spline-based rivers are used. Main part of this is just like making sure your map can handle rivers. Second part, simulating the river and reviewing it. So here you're just running the shallow water simulation, seeing what it looks like live in the editor, and just sort of modifying your, you can move some collision objects around and things like that, and just change simulation parameters however you want in order to get the results that you want. And finally, once you're good with your simulation, you bake it with just a button, and that propagates the data to all of the water bodies in your map, and you can preview it. And a lot of times, you're not done just there. You have to repeat this process because water might flow over some area. You might have to make some changes somewhere. So it's definitely an iterative thing. So here we'll just talk about the modeling phase. And this is sort of an illustration that we saw from the keynote that demonstrates the flow of the river and what happens when you move a collision object. So here, during the modeling phase, you have some rocks as colliders, and you'll move them around in your map. And you'll get different flow depending on where you put those objects. And the flow will adapt to these types of things. And we found that you can get really interesting results by just moving rocks around in the river, just like a normal river. Depending on where rocks are, you'll get like different types of rapids and things like that. And that's something we'll definitely discuss later on when we talk about the chaos integration. But purely for visual uses, like in the Witcher 4 thing, also really important to just place them to give interesting results. Also, really important thing that doesn't really illustrate it here, but anyone who's run fluid simulations know you can't really predict what they're going to do before you start it. So you might model your landscape, have your height field, run the simulation, water spills out over the side. Pretty common thing. This is where having that iterative workflow is really helpful because you can change it and put a rock in where it spills over or change the terrain a bit, that kind of thing. So on the Witcher 4 demo, we had 2 simulated rivers. Each of those 2 rivers was comprised of between 2 and 4 spline rivers, or spline water bodies. And those all kind of had branching, so they all met to one water body and then flowed into the main river. You can kind of see running top down on this image. And that main river there was not simulated. That was just a normal spline-based water body. But the ones in pink were all simulated. And we definitely had a lot of iterative work with CD Projekt Red on the terrain, because they modeled the terrain and then you'd run a sim and the water would spill over or something like that. And you have 2 dueling things here. You have what the art direction is and what the artists want to do, and then you have what the simulation wants to do. And you really have to meet somewhere in the middle to make sure that both work well together. So we added a lot of controls for that, like making sure that you can push the water towards the spline in case it flows over, and just find other ways of working around that. So all of this work is controlled by this new actor we introduced called the Shallow Water River Actor. It controls everything related to the simulation and baking process, and we'll just give a quick overview of it here. So at the very top, in purple, you have just these buttons that are very useful. You can bake it with one click. You can reset the simulation with one click. So maybe you make some changes to your landscape and you just want to rerun the simulation. You press reset, and it kind of handles resetting everything with your simulation. Otherwise, like when you just have your Niagara simulation, you put it into a scene, sometimes it can be kind of tricky to kind of manage all of this and make sure that everything works correctly. But we kind of made sure that that was all encapsulated really nicely in this actor. So next, going from top down, all the simulation parameters. Like I said, this is all driven by a Niagara Fluids simulation. So it's a typical shallow water simulation from Niagara Fluids, and tuned for some specific things related to the baking process and working with spline-based rivers. Same basic thing though. Anyway, so we have some parameters here that all connect to that Niagara simulation, and you can change them here for convenience. Note that for those of you who are used to using Niagara, you can also just open up Niagara itself and play with it just like you would with any other Niagara system. So the next section's probably the most important one to change first, because it's the only one you really need to make sure to do before you get any results, is what are the source water bodies? So this is where you connect up the ones in your map that you want to simulate. And once you connect that up to here, it'll kind of take over the material assignments and things like that, because the whole purpose of this actor is to act as an interstitial between the simulation and the water bodies to make sure that they render the live sim, render the baked sim, do some debug view, things like that. And finally, something that we'll go into a little more is the collisions. So collisions are definitely the key component to this for getting good visuals. And if you've run fluid simulations before, you know that is like the crux of running a good fluid sim is really good collisions. So here's where you set up your collision objects. And to go into it a little more detail, we do collisions based on a number of things, but it really all comes down to making some height field that lives underneath where the water will simulate for the water to flow along. So we'll use landscapes, you can use static meshes, and you basically just can tag them or add them to a list. Sometimes you might want to dilate them. So when we say dilate, what we're doing is basically making the collision object a little bit bigger. And you might want to do that because we noticed on the Witcher stuff that sometimes the water would flow through the colliders. And that's just because when you generate the height field for the collision objects, you don't get quite what you expect. So you have all the controls. And here we're just showing a debug rendering where you show the collision surface in orange. So here we have, in addition to that orange view, we have other rendering states that kind of take control of rendering the river to show you different views of it. This first one on the left is just the water component. The water component is what you would get normally if you were just rendering the water bodies themselves with no simulation. So when you're editing the spline points, you often want to have it in water component mode because then you can just see kind of this very simplistic view of it. In the middle, you can do the live simulation, so you can see the propagation of the flow. And on the right, the bake simulation, which is what you use in-game and is a super optimized view of everything. Okay, so next we're going to just talk about the water simulation concepts that work behind the scenes here to get the results. So everything here relies on shallow water simulation. Shallow water simulation is a 2D fluid simulation technique that just generates a height field that describes the fluid state. So you get the fluid height, and there's some amount of depth associated with it, and a two-dimensional velocity vector on that surface that represents the flow velocity. And so this is something we've had in Niagara Fluids for a very long time. We're using the same basic simulator we've always used. In this example we're showing here, we have ripples coming off of a character using shallow water. It's a pretty robust type of simulation that lets you do things from ripples like this to rivers. So the same core architecture can be used in a lot of different scenarios. Okay, so this is just imagine a slice through that two-dimensional domain. This is roughly what you get where you have water and collision objects, and we're just saying it's a landscape here because that's generally what you're dealing with. So in blue, that's your water. It always lives on top of the landscape, and you get columns of water. You have one column of water per cell. You can't have multiple heights per cell. This is purely a height field fluid, and it's an important thing to remember because that means you can't have water flowing under and over a collision object at the same time. You only get one. You can only flow over things, essentially. It's the easiest way to think about it. And then in orange, we have the landscape. So in this case, this is where the water will flow. Imagine you're emitting water from the left. You'll get water that flows down this landscape and fills the domain. One really important thing to note here, the left two most cells don't have any blue above them. That means they're empty, they're just dry cells. So a lot of times when you think about shallow water simulation, you refer to dry and wet cells. And it's an important thing to note because there's just different things you need to do whether you're considering a dry or wet cell. And that is definitely true with every case with simulating rivers is not every single cell in your simulation has water because you're only flowing where the river basin is, that kind of thing. So here is a very common problem with shallow water simulation that we did some improvements for with developing this baked workflow. So on the top, you have a very common artifact you get where you have sort of sizzling, popping parts of the water surface that don't look realistic at all. And this is because shallow water is inherently quite unstable, especially in cases when you get it to be too deep, too fast, or your simulation cells are too small, or just some combination of those factors. So a lot of times you run a shallow water simulation for a river flows, generates like a pool somewhere, you don't know beforehand how deep that pool will be. So you'll get problems like this. And what you do is there's just some techniques that we use for making sure that you just cap the maximum depth of the water that you integrate with. And by doing that, you can help really isolate and reduce these high amplitude waves that you see in the top video, and they basically just disappear in the bottom one. And just to note, this is not something you really need to worry about. If you use this tool set, it sets it automatically for you. So just something behind the scenes. Also, a lot of times you have this problem with running river simulations where you get these thin streams of water that run along the landscape that don't really act realistically, because in reality, you wouldn't have a thin stream of water that just sort of like flows as fast as it does, and it's just some limitations of the algorithm, the core bit of the algorithm. And we introduced just friction using Manning's roughness coefficients. These are kind of interesting. So hydrological studies have used these for a long time to just sort of describe the like macro properties of that bottom contour that water flows on. And these units don't mean anything for practical use with what we do, but I just really think it's interesting that they make distinctions between concrete channels and saltwater marshes and things like that at this sort of like very macroscopic scale. So anyway, we use this idea of having friction that's just based on the water depth that lets you change how fast water moves in very shallow areas, and it really helps make the river simulations more stable. Okay, so in the next part, we'll talk about the stuff that really brings this all to life with the rendering and secondary particles. So there are a couple components that we use here in that Witcher 4 demo and what's in the engine for advecting FFT waves, which gives surface ripples that move with the flow, advected foam, which is just what you might expect is sort of like white frothy areas of the water that have been churned up, and then also spray particles that use Niagara simulations to propagate just things that leave the surface and just add more three-dimensional detail to this 2D water simulation. So the first thing we'll talk about is texture advection. So this is what moves waves along the surface of the water. So the water surface, when you bake it out, is a deformed plane that has velocities on it. It's just a static velocity field. Because you bake it out when it reaches a steady state, you only have one velocity. It's not a time series. And the idea is that you want to use that velocity field to push some texture along it. And this is a pretty common problem in computer graphics. You get stretching. You get problems with it. So that's something we need to deal with. And so the first thing before we have to figure out how we deal with the stretching when you advect that surface texture is what is the texture we advect? And we use FFT waves. This is something commonly used for oceans, but pretty easily adaptable to stuff like rivers by just changing all the parameters of the FFT simulation to just suppress all of those really suppress all of those low frequency waves like large ocean swells. And if you kind of play with it enough, you can get a little patch that looks pretty good and is just only those sort of more high frequency details that you would get in a river or a lake or things like that. And note, because, especially because it's FFT based, this is a repeating texture that tiles very nicely. And note that we could do two things. We could bake this out to an atlas, or you could use it live. And in our system, we chose to use it live because the FFT is quite fast, and it uses far less memory than having some baked out atlas where you have to worry about how it loops and things like that. So keeping it live adds a lot of detail and doesn't have it repeat. It works out really well. So now we want to make sure that we can push it along the surface. So with making sure the advection works well, you can't just sort of take that water texture, the FFT patch, and just push it along the velocity field. It'll stretch out and it won't look realistic. And this is because unlike the spline-based rivers, the velocity field you get with shallow water is very rich. There's a lot of detail. There are places where the flow does things that will naturally just stretch any texture. So in order to deal with this, we do a lot of texture blending. So in this example, we kind of are trying to illustrate part of the river from the Witcher 4 demo and advecting several different texture UV sets that are reset periodically. And the idea here is that you let the fluid push that texture along, and then you reset it at some point. And when you reset it, there's no more stretching. And you don't notice a pop in it resetting because you have another one that picks up. So you're constantly recycling these sets of UVs in order to make sure that you don't get any stretching. But you do end up still getting stretching. There's no way to get rid of the stretching completely using this unless you do other additions that are more expensive. So you end up getting stretching, but it's far minimized than just doing just sort of naive texture advection through this, this fluid field, velocity field. So in order to combat that, there's another technique that we use called texture bracketing. And this is a very different technique, and I'm talking about it very briefly here. I highly recommend looking at Hugh Bowles' shader toy example for this for more details. But the core idea here is that you discretize the directions you advect along, and then advect the fluid along those directions and blend them. So if you have a velocity that's moving, you take the two closest directions on either side. Imagine there's cardinal directions on a compass. Advect along those cardinal directions, and then based on how close it is to each one of those, you just kind of lerp between them. And the end result of it is, and you can kind of see it here, is you get the texture slides over itself, but it's not stretching. So in this case, you have a different artifact, but this artifact is, in some cases, less objectionable than the stretching. So obviously, we can't just use one of those, but we use both of them together. And in cases like this, where you have much higher frequency detail than something like that, that checkerboard, you don't really notice it. So it works pretty well. And as you might expect, there's a million controls for it, but generally you don't need to touch them too much because it'll just work for the types of rivers we have. There are cases where it does break down, but it works pretty well as a general purpose tool. Okay, so that kind of establishes how we do texture advection, and where we talked about it for the surface waves. So in addition to surface waves, we also have foam that you want to advect on the surface. And here is a very exaggerated image of the foam. This is not what's in the actual project, but I just kind of wanted to make it look as obvious as possible up on the big screen. So foam is just another texture. It's no different than the water surface detail, it just lays on top of the surface. And the question is, where do you put foam? Well, pretty common techniques for this is you just derive different quantities from the fluid velocity field and use that to sort of use as your emission criteria for this foam mask. And so in this case, we use curvature and vorticity. So in purple is curvature, and you can imagine curvature is really just isolating those places where the fluid flow changes direction pretty quickly. So where I have circled is water pouring over a rock and then continuing downstream. So you get a discontinuity there, not really discontinuity, but a very sharp point. It'll isolate those sharp points and say, hey, this is probably where we should have some whitewater. That doesn't encompass all the areas that you would see whitewater. Another common place that you would be places of high vorticity. So in the more pinkish color, this is a place where you have high vorticity where the water is spinning. So vorticity will give you a measure of how fast the water is spinning in any area. And this will help isolate things like eddies or other rotational components to the velocity field of the fluid. And also, one thing I should mention, these are blended together, and you can kind of change the magnitude of like which one contributes more to the foam mask. So it's a very flexible system for it. And you also use that same emission criteria for spray particles. So in this case, we are emitting them mainly from curvature, but you could emit them from other things too. And the thing to note here, this is an example from the Witcher 4 demo. We had to use masked opaque sprites for the whitewater. That is by far the fastest way to render whitewater. It's a little unfortunate, because there's only so much you can do with masked opaque particles, and it makes it really tricky, but you can get a nicer look when you use transparent particles too, or meshes. So there's a lot of flexibility with the system to change how you render the foam, the spray particles, and you can get different looks from it. So here's just an example of the river with the whitewater particles mixing with the foam. And one of the things that we had to do was really make sure that the whitewater and the foam, the whitewater and the spray particles kind of mixed together nicely because they're very different textures and very different materials used. And in this demo, we had just wildly different lighting conditions, and it was very challenging to get things mixing together really well. And this is just all of the layers put together. So again, like in this case, we have those fairly opaque masked particles that are used for the spray particles and mixing them with the foam. All right, so in the final part of this talk, we're going to go through chaos integration. This is something that was not used on the Witcher 4 demo, and is something that we've been working on for a separate demo. So the chaos integration is using that baked fluid surface and the velocities to drive rigid bodies. So we have this really compact, nice representation of the river from the baking process. And because it's a static velocity field, it's very easy to just use it as an array. And it can work with networked applications or anything that chaos supports. So there have been previous integrations of buoyancy in the engine that use more simplistic models. So either just spheres like pontoons that live on boats, or boxes for chaos integration that really only use the velocity of the fluid sampled at one point on the box. So in cases like that, you can't support rotating velocity fields where you might have the fluid flow spin an object, and the drag model didn't support things like using the actual shape of the object. So in this case, we wanted to generalize and make sure that we support 1, convex hulls, and 2, complex river flows. And obviously, making sure that it is performant and can handle multiple interacting bodies at once. So we make some concessions for accuracy to make sure that we can handle the types of things that we would have in general case experiences built with Unreal. So here's just a little bit of math. Doesn't really matter too much if you look at it too closely. But the force computation for saying, how do we use the fluid flow to impact a rigid body has a lot of parameters to it that you don't need to worry about as an artist or as a developer, but show the complexity of this model that we have. So it depends on the area of the object. So if you have something that is really long and thin, it will behave different than something that's more pancake shaped. We're doing things like computing the volume of that object below the water surface and utilizing the fluid velocity sampled across the entire surface of the object to do a surface integral to get a really accurate representation of how the fluid impacts the object regardless of the shape. So we'll go into a little bit of detail about the algorithm we use for computing that force. Here we're showing a box in that orangish color. That could be a convex hull. Normally when we use this, you end up using a convex hull. It gives much better results without a huge amount more cost, but the boxes are very, very efficient to do too. And what we do is we compute a single water plane per box. So in this case, you have a water plane that spans across really the bounds of the box. And we do one water plane per box to just make the algorithm more simple. It'll become more clear in the next slide. And so we sample that water height, we sample the water normal, and use that. And note that in practical use, you often have more than one shape per rigid. So in that case, you'll have one water plane per rigid. So you can get much more complex interaction with the water when you have very large objects or things that are, have just very detailed shapes. So first thing you do after you have that water plane is you compute the intersection points of that water plane and your box, or imagine it's a convex. And it's really the same integration code regardless of box or convex hull. And the next thing we do is we compute the volume and area of each face below that water plane of the object. And this is really important because when you do buoyancy forces, you need to know how much of that object is submerged under the water to be able to push it up out of the water. And so this generalizes to convex hulls really nicely too. It involves like making this sort of fan triangle distribution, tessellation on the object below the water surface. And this is also sort of where we start sampling the water properties like the depth and the velocity in order to make sure that we can interact, have that velocity transferred to the rigid bodies. And one thing to note here, I said we have one plane per object. You can imagine in theory that instead of having one plane that gives sort of this very approximate integration, there are algorithms out there that have a very accurate intersection between the water surface and your convex hull. The downside of that is it requires a lot more computation and often involves like reteslating your convex hulls to match the tessellation rate of your simulation, which for very complicated simulations can be very expensive and often not worth it because in very flat areas of a river, it doesn't really matter that much. And even in other areas, it's not that important because a lot of these forces involved are fairly low frequency things compared to collision events you get for just hard geometry. So as the final step, we come up with the force you apply to the body. So in yellow here, we have the force you apply. Obviously in blue, that's the fluid velocity. So depending on a bunch of those parameters that we just calculated, you come up with some force for the object. Here are some practical examples. So here we have boxes of different densities. And some of you might remember back to grade school, you talk about Archimedes' principle. So in red, we have an object that has a density of 0.5 grams per centimeter cubed. And half of the object is above water and half of it's below water. As you move to the right, those two have very low density. And they sit very high up on the water. Note that you do get some instability with really low density things. And that's something that, at least for now, you need to be careful of if you're using the system and make sure you dial in what density basically the highest density you can get away with for your object that you want to simulate. And as we move left, you get different properties. An interesting thing is the second one from the left is neutrally buoyant. So in this case, it's the same density as the water. And if any of you have gone scuba diving, often you'll adjust your density as you're diving to make sure that you float in the water without moving up or down due to buoyancy. So you can kind of get that kind of effect too. This is a very simple example of the drag model that we use. So with this drag model, the really important thing to note is the surface area in the direction of movement matters a lot. So both of these boxes have the same initial velocity and start at kind of the same point, but one of them propagates much farther than the other one. This is because the aerodynamic drag has a really big impact on how fast it approaches the velocity of the water. And so in this case, the water is just still. So it's just like how fast does it come to rest? And this property works not only for surface velocity like this, but also for buoyancy too. If anyone here has ever like jumped into a body of water, like into a pool, if you do a pencil dive and just kind of get really straight and just jump in, you go way deeper in the water than you do if you make a belly flop. And this is the same principle at play here, and you'll see that in the example we give a little bit later with the demo we created. So in addition to the drag model, a really important part of this is applying torque, and this is something that was missing from previous algorithms. So here we have a constrained rigid body that can only rotate and is sticking down into the water. And it's rotating because of the velocity of the river passing underneath it. So you can make things like water wheels. And this is kind of a cool thing you can do where you can start making some like emergent gameplay elements that power things based on water. And it's actually quite fun to play with and just like make little things that sit in the water and like move because of the fluid flow. Okay, so now we're going to talk about gameplay. All of these elements combined together make for some really interesting opportunities. So here I have an example of myself paddling some whitewater back in 2012, before I worked at Epic. And it's a river in California called Cache Creek, one of my favorite places. And this is the final rapid in the river that's really hard, called Mother. And it's a pretty exciting thing to do because you have to adapt to how the fluid flow affects your boat. You're constantly reacting to it and changing the way you're paddling. You never know exactly what's going to happen, and you really feel connected to the water. So that's something that I thought was like, man, that is a really neat thing that we might want to encapsulate in games. And also, another thing that makes it a really unique experience is this idea of unpredictability. So at the bottom of this rapid, there's a little beach on the left, and you can see a bunch of boats there. People just pull out of the river, grab a beer, and just watch the carnage where everyone's falling out of the raft. And it's like a great place to see it. It's quite entertaining. One time, my wife, who I do most of my whitewater with, took her very adventurous mom out with us on this river. And they were ahead of me, and I was paddling, and all of a sudden I look to my right, and I see my mother-in-law clinging to some grass on the side, and the river was trying to pull her down, but she's holding on. And I said, are you okay? As I float past, I can't stop. You can see what the river looks like. It's like really quite strong. And she just said, I'm fine. And wasn't able to help. She ended up just floating down on her back. She was totally okay. She had a great time. And it was really memorable for all of us. So really want to capture these sort of very emergent properties of whitewater rafting in a game because it's unpredictable, it's fun, and it makes you feel connected with the environment you're in. So this is the demo we built. And this is something you can see on the expo floor. I'll be there after this talk, and you can come talk to me. I can show it to you. So this is just stress testing everything that we have combined together in this one demo. So we have the Baked River workflow. We made this river canyon with PCG to scatter geometry, some of which is used as collision objects. And I really tried here to design the rapids by moving rocks and changing the gradient of the river to give things that felt realistic and at least inspired by what I've experienced in real life. And all of the boat dynamics here are driven by the chaos integration I mentioned before. So when you paddle, the only real thing we define there is what is the paddling motion. And everything else is just derived from physics. So all of the gameplay is like completely emergent, having to like navigate the rapids without flipping the boat. You'll notice here, I don't flip the boat. It is very easy to flip the boat. I just ran it until I didn't flip the boat. And so the drag model that we talked about earlier can spin the boat around if you get on the side, and there's an eddy that kind of rotates you. You can see right there, I just start to rotate, and you have to counteract it. So you're always like reacting to the river in like a really dynamic way. And it's really fun. It's really interesting. And so the other component to this that's a little removed from what we've talked about is there's a lot of chaos integration to get that character working. So there's a bunch of constraints that keep the character's hands on the paddles as you move, and some really interesting interplays between that chaos integration with the water and the chaos like constraints that keep that character working. And so I have to give a shout out to a whole bunch of people. This was not just me that worked on it. Jim Van Allen did a lot of work to get the rafting working as like a gameplay element and get the character in the boat and all the constraints set up. Stephen Barnett helped tweak the raft controls and all the drag. We worked a lot together on it. Tim Brackenseek did the raft modeling and surfacing and all of the geometry of the raft. Claire Smith did sound. Jack Oakman did the environment modeling. Dan Pearson and Jonas Anderson did some shader work and spray particle work. Cedric Khalad and Bryce Criswell and Michael Baylog really helped out with supporting this project, and it was really fun to work on. So yeah, you can come find me on the expo floor. I'd be happy to show it to you and go through it, show you the project too. And so in the future, we'd love to do other things too. We'd love to improve that drag model, just support other things with it. There's a lot you can do. There's also a lot we can do to just improve the general rendering of the foam and the water surface. Just taking a pass over all of that and really making sure we can dial it in really well and just add some other features that we've been playing with. And here I just wanted to show something as just a teaser example of something I'd really like to do that's not ready for production whatsoever, or even a talk, is the idea of coupling for 3D sims. So in this case, we have a 3D flip simulation for liquids and this ellipsoid that both makes splashes and can be affected by the water as we move the boxes. So I think there's a lot of other types of things that we can make with 3D sims. Obviously, very expensive, but mainly just for the purposes of seeing how far we can push water-based emergent gameplay. And here, if you're interested in any of the references we use, recommend taking a picture of it, or just you can come ask me and I can give some of this info. But there's a lot of really good literature out there on this topic. And I kind of picked and choose the things that worked really well for this. OK. Yeah, and thanks to all of you. And yeah, please come by the expo right after this, and I'd be happy to give you a demo. Thanks. If there's any questions, yeah, feel free to come up to the mic.